Alright, now that we have indicated the periodicity of the system for discrete time periodic signals, the periodicity in frequency domain, I mean, it's a good idea to see the relation between the impulse response and the frequency response, because we need the frequency response h omega so that we can all multiply our Fourier series coefficients with the corresponding value of h of omega at the corresponding omega frequency. Before that, maybe we should remember what it was for the continuous time again, so that we can find the relation or the similarity in between. So we have to find the relation between h of n and h of omega. Let me turn to black. Okay. So this is what we need to discover. First of all, in terms of h of t, it was something like this. H of omega in continuous time systems. H of omega formula was an integral from minus infinity to infinity h of t e to the minus j omega t dt. Alright. So this was the formula for the reconstruction of h of omega, the frequency response, from the impulse response. H of t is the impulse response. That was the relation. Now, in our book, and in many of the books, this h of omega is not indicated by h of omega in order not to confuse with the continuous time and the discrete time. Otherwise, we can always say in continuous time it is h of omega, in discrete time it is h of omega. But let's put a differentiation in between. They say that in continuous time the representation is h of j omega, and that j is nothing but the j right behind omega in the exponent. Okay, it's just a notation. It means h of omega. J is not a variable, it's a constant. And the new notation of h of omega in discrete time comes with a summation, of course, because we cannot integrate. We don't have an h of t to integrate with dt. We have h of n, therefore it will be a summation of n from minus infinity to infinity, which is the impulse response range, hypothetically at least. We have h of n, and the same complex exponential, e to the j omega n. Not omega t, but omega n. So they look like each other, right? There's not much difference. But again, this has its own representation, and the representation is a little bit difficult to write, a bit longer to write. It's h of e to the j omega. It means h of omega, okay? The only variable here is omega, the frequency. The others are e and j, just inside the notation. Don't worry about that. So these two will differentiate between the continuous time system response, frequency response, and the discrete time frequency response. So from now on, if I give you h of e to the j omega, it means it corresponds to a discrete time frequency response, not a continuous time frequency response. But the names also indicate something, but it gives you a hint about the periodicity of these as well. Notice that the top argument is h of j omega, and omega ranges from minus infinity to infinity. In fact, omega always ranges from minus infinity to infinity. And that's also valid for the second one, but look at what happens to e to the j omega as omega changes from minus infinity to infinity. E to the j omega is periodic with 2 pi, isn't it? If omega is equal to 0, it will be e to the 0, which is 1. If omega is equal to 2 pi, it will be e to the j 2 pi, which is again 1. So this expression indicates that everything here is 2 pi periodic, including the frequency response. The frequency response is also 2 pi periodic. Okay? So that's the difference. Now, what you need to do then is like this. If x of n goes into a system and y of n comes out, if this is your situation, and that's the whole concept, in this situation we have the corresponding a case here and the corresponding h of e to the j omega here, and the corresponding, let's say, b case, the new Fourier series coefficients. And the formula for the new Fourier series coefficients are bk is equal to ak. By the way, they have the same fundamental frequency. If the frequency of a signal is omega 0 at the input, after passing through an LTI system, linear time invariant system, the frequency, the fundamental frequency of the output will also be omega 0. It doesn't change. A sinusoid comes in, the same frequency sinusoid comes out. If a rectangular shape comes in with a frequency, something comes out which will also have the same fundamental frequency as the rectangular input. And b case will be equal to ak times h of e to the j omega at the corresponding omega. What is that? The corresponding frequency is omega is equal to k times the fundamental frequency. So that is the kth harmonic in other words. Ak is the scale of the kth harmonic, and k times omega 0 is the frequency of the kth harmonic. So that's how things work. Let's see one example. And that example is as follows. Suppose that we have an input signal x of n, which must be periodic, of course. So I'm going to give you a simple periodic signal, because otherwise, as you remember from the previous example, even the simplest examples will have a lot of algebra. So let's avoid them. It's a simple sinusoid, it's a cosine. And we have a system with impulse response. So if I give you impulse response, you are obliged to evaluate the frequency response then. Okay. Which is this, alpha to the power n u of n, where alpha in magnitude is less than 1. Okay, that's a good point. Look at this h of n, and let's remember some exam questions. If I give you an impulse response like this, what would you say about linearity, time invariance, causality, and stability? The answer to the first two, linearity and time invariance, is obvious. Why? Because I'm giving you the impulse response, and the impulse response concept is valid only for linear and time invariant systems. It can't be anything else. So if this is an impulse response, if you have an impulse response, you say that it is linear, L / time invariant. They are certain, because this is an impulse response. So the only two things that you have to consider are, is it causal, is it stable? Is it causal? First things first. It is causal because the impulse response exhibits itself, shows itself at the point and after the impulse. The impulse comes in the center and the response comes afterwards. If you have, because of u of n, if it is, for example, u of n plus 1 or something like that, then it would be shifted towards left, and that means that the response came before the impulse. That would make it non-causal. But this one is causal. If you have a u of n in the impulse response, certainly, or u of t in the continuous time, certainly it is causal. Because the impulse response is right-hand sided. Just draw it, you will see that it's right-hand sided. Is it stable? Is the next question. It is stable. Because the infinite series sum, if you sum them up, for alpha less than 1, alpha to the power n summation from 0 to infinity is equal to 1 over 1 minus alpha. And if alpha is, let's say, 0.5, then the summation is 1 over 1 minus 0.5, which is 2. So it is absolute summable. If it is 1, then alpha to the power n will be 1 always, and the summation will be 1 over 1 minus 1, which is infinity. So it's going to diverge. If alpha is greater than 1 in magnitude, it's even worse. It's a growing exponential, so it doesn't converge. But this one is cos-length stable, and it is, of course, certainly linear and time invariant. So that was a parenthesis. Let's now think of how to find y of n. And I'm asking some curious students who have a lot of time at home to try to convolve these two. You should convolve, right? In order to find the system response. You convolve the input with the system response. The only problem that you will encounter is that both the system response and the input signal are infinite extent. And the convolution is a mess. I mean, you cannot do that. Just try. You will see that it's not possible. So the only way to find the output is by finding the Fourier series coefficients of the inputs and multiply them with the corresponding frequency response. And for that you need to find the frequency response. And the frequency response formula is here. It's here. Summation from minus infinity to infinity hn e to the minus j omega n. So let's try to evaluate that. And the result will be h of e to the j omega, which is the frequency response. Summation n from minus infinity to infinity h of n e to the minus j omega n. This is our formula. Now h of n is alpha to the n u of n. Because of this u of n, the summation starts from 0. Right? Because before 0, h of n was 0 to infinity. And now I can replace h of n with alpha to the n u of n, but the range is already from 0 to n, so let me write only alpha to the n, and then e to the minus j omega n. Do you remember what I have told you in the previous hour? I said that you need to become familiar with power series sums and things like that. This is another case which requires summation and from 0 to infinity. I want to put the common terms into parentheses. Alpha times e to the minus j omega to the power n is what we have here. And that alpha times e to the minus j omega is this famous x. What was the summation from 0 to infinity x to the n? I just told you the answer. It is 1 over 1 minus x. So this one is 1 over 1 minus x. Are you happy with this result? It's 1 over 1 minus x. And it is convergent, and the series summation is not infinity. It's not a growing summation, because the magnitude of alpha is less than 1, and the magnitude of e to the j omega, or e to the minus j omega, is 1. So the overall magnitude of this whole x, the magnitude is alpha, which is less than 1. Therefore, its series sum converges, and the converging magnitude is there. It's not infinity. It's not global. So we found our filter. This is our filter. Okay, 1 over 1 minus alpha times e to the minus j omega. It looks a little bit complicated, but no problem. Whatever h of e to the j omega is, it is this. And it's here. So now we can safely represent our x of n as 1 over 2 e to the j 2 pi over capital N plus 1 over 2 e to the minus j 2 pi over capital N. Right? It was a cosine 2 pi n over capital N. So this is A1, this is A minus 1, and omega 0 is 2 pi over capital N. These are the necessary things. You need to have AKs, omega 0, and h of e to the j omega, or h of omega. So what is B1? B1 is equal to A1 times h of e to the j omega at omega is equal to k times omega 0, which is 1 times 2 pi over capital N, which is 2 pi over capital N. And B minus 1 is equal to A minus 1. The only non-zero terms are these. The other Fourier series coefficients don't exist. H of e to the j omega multiplication at omega is equal to k times omega 0. K is minus 1. So it is minus 2 pi over capital N. So these are B1 and B minus 1. And what are they? Let's see. B1 is equal to 1 over 2 times, what was the formula? 1 over 1 minus alpha e to the minus j omega. 1 over 1 minus alpha e to the minus j omega. Minus j, of course omega must be equal to the current omega, which is 2 pi over capital N. 2 pi over capital N. This is B1. And B minus 1 is equal to 1 over 2 times 1 over 1 minus alpha e to the minus j omega. And omega this time is plus, omega is this time minus 2 pi over capital N, minus j omega will be therefore plus j 2 pi over capital N. Alright? So these are B1 and B minus 1. So what am I going to do now? I have to say that my new signal y of n is equal to, let me open a big parenthesis, 1 over 2 times 1 over 1 minus alpha e to the minus j 2 pi over capital N. This is the first harmonic, first Fourier series coefficient, and it must be multiplied by the first harmonic at the corresponding frequency, e to the j 2 pi over capital N, plus the second Fourier series coefficient, b minus 1, that is, 1 over 2, 1 over 1 minus alpha e to the plus j 2 pi over capital N, times e to the corresponding frequency is minus j 2 pi over capital N. So it doesn't fit into one screen for me, sorry about that, but this is y of n. You can leave it like this, and you will still get the full credit if it's an exam question. Okay? But again, for the mathematically curious, this has a compact form, because now you have to be aware of one thing here. This thing and the other component are the same with complex conjugate pairs, and that is the complex conjugate pairs only appear at real sinusoids. For example, if it's a cosine, 1 over 2 and 1 over 2 are conjugate pairs. 1 over 2 complex conjugate is 1 over 2. For the sine, 1 over 2j was one coefficient. What's the complex conjugate of that? Minus 1 over 2j. So for the sine, they are complex conjugates of each other as well. For real sinusoids, it's always the case. These two are always complex conjugates of each other. for the opposite frequencies. This one is for frequency omega is equal to 2 pi over n. The other one is at minus 2 pi over n. So we expect a sinusoid from here, and that sinusoid, I'm not going into the details of that, I'm just going to write it here. If you want to expand using Euler's expansion and such, you will see that they correspond to the same thing, interestingly. Will be equal to 1 over square root 1 plus alpha square, a cosine 2 pi over n minus, that's interesting, an arctangent of alpha. Well, that's a phase, and alpha is the amount of the tangent shift. Therefore, the amount of phase corresponds to the arctangent of that alpha. And it's the same cosine as the input, by the way. Look at that. What was the input? It was cosine 2 pi n over capital N. And the output is again cosine 2 pi n over capital N. Shifted by something and scaled as well. It's a little bit attenuated. It's not amplified, but shrinked. Okay. So this is the way that this system or filter acts. It still produces a cosine with a shift, with an amount of phase. Now this much corresponds to the whole thing that we need to talk regarding the Fourier series coefficients. So in order not to confuse with the rest of this lecture, I'm not giving an answer. We didn't finish, but I'm